All right, so tonight's speaker, Dr. Lindy Elkins-Tanton, she's the managing director and co-chair of the Arizona State University Interplanetary Initiative. So she is at Arizona State, of course. She's a planetary scientist, and her research includes theory, observation, and experiments concerning terrestrial planetary formation, magma oceans, which some of you may be familiar about with the moon, and subsequent planetary evolution. She also promotes and participates in education initiatives, and in particular, inquiry and exploration teaching methodologies, and leadership and team building for scientists and engineers. She's led 4 field expeditions in Siberia. That in itself is fascinating. And I'm sure it's a whole other talk on its own. She's also done field work in Sierra Nevada, the Cascades, Iceland, and the Faroe Islands. She did her bachelor's, master's, and PhD from the Massachusetts Institute of Technology. She's also been a researcher at Brown University, and again, back at MIT. And she was also at the Carnegie Institution for Science, and she moved to her current position at ASU in 2014. She's been on a number of panels, a number of different awards and stuff, and I could take all night listing those if I wanted to, but you can go check out her profile on the ASU website to see more about that. She's also given a TED Talk. How great is that? So tonight has to be a good presentation if she's done a TED Talk.
There's TED X Talk. It wasn't a main stage TED Talk, so lower the expectations.
Well, sorry, it's already out there, Lindy. So it's all on you. And she, of course, is also the principal investigator for the Psyche mission, which was selected in 2017. And that's what she's going to tell us about tonight. So when you're ready, Lindy.
All right, let's see if I can get this sharing up and going. Share this. And just let me know if I need to swap the screens, or is it correct?
We're good to go.
All right, perfect. Well, thanks an awful lot, everyone, for coming to hear about the Psyche mission, and Andy for such a nice introduction. So I'm gonna tell you tonight about Psyche. Psyche is both the name of an asteroid that orbits the sun out between Mars and Jupiter, and it's also the name of the mission that we're sending to investigate this asteroid. And what you see right here is an artist's rendition of Psyche. And this is important to remember because it's one of the really amazing things about this asteroid is we do not know what it looks like. We're really exploring for the first time. So human exploration in space, we have visited either in this case with humans or with robots, quite a number of rocky planets. Here's the limb of the moon. This is the Orientali Basin that we can't normally see from the front. Hang on a minute, just gotta fix my screen. There we go. There's Mars and one of the wonderful cliffs of Mars being investigated by a rover. So rocky worlds, here's an icy world. This is Europa, a possible host of microbial life we hope to discover one day. So rocky and icy worlds and worlds made of gas like Jupiter. But we have never visited a world that seems to be made mostly of metal. And that is what Psyche is. We think Psyche is a metallic asteroid, largely made of metal. And so how would that happen? Here is a little schematic of how we think that planets are built up. Just in the first 5 million years of the solar system, the first blink of an eye of our solar system. On the left, you see little bodies called planetesimals. These are bodies that are just tens to hundreds of kilometers in radius, small. And they accrete together into bigger bodies called embryos, and these would be things maybe the size of Mars, and then finally up into full-fledged planets like the Earth or Venus. And you see in the middle of 3 of these planets something black, which is meant to indicate that it's the iron-nickel metal core. On the planet on the right, which could be the Earth, say, we've got an iron nickel metal core, and then the outside in green and red is all rock, silicate rock. I'm imagining here that this one has just experienced a giant accretionary impact. It has a red magma ocean around it. But the main point here is that 3 of these bodies have differentiated. That is, their metal has sunk to the middle to make a core, and their rock is on the outside, the same structure that we have on the Earth today. And 2 of them, the 2 littlest ones, I mean to indicate that they haven't been through that process. They didn't heat enough that their little tiny pieces of metal melted and sank to the middle to make the core. This story of differentiation is, we think, the story of Psyche. And so this is our leading hypothesis for what Psyche is. And let me show you a cartoon. We have been able to work throughout our process from proposal onward with the Hollywood artist Peter Rubin. We knew when we were proposing this mission that we needed to transfer the sort of video, the imagining of the process that created Psyche, or as we imagine it, from our minds to the minds of the people who were reviewing the proposal, so that they would understand what we thought this bizarre body was. And so we were fortunate enough to work with this artist who helped us out. So here's our best guess for what Psyche is in 9 cartoons. So you start at the top left, and that is a planetesimal, like from my previous picture. In this one, the iron nickel core is still molten, and it's shown as hot red and orange liquid metal with rock around it in brown. We imagine that this planetesimal experienced some destructive impacts. In the early solar system, our best guess is that many, many bodies were colliding a lot. and some of them collided and stuck together and built up to become the planets that we see and know. And some of those collisions, though, were destructive collisions that actually broke apart the impactor and the impactee, rather than making them larger and growing up into planets. And so in picture 2, in the top middle here, with the little POW that I asked Peter to leave in there, just because you talk about things like cartoons, I really loved it. We think that if they were between 4 and 8 destructive collisions, then a lot of the rocky outside might have been knocked off of this planetesimal, leaving only the liquid metal core in space, and that's number 3. And in number 3 and number 4, you can see some of the rock falling back down onto the surface, because it wouldn't be stripped perfectly. And in 4, this spinning molten metal body creates a magnetic field, and we show the magnetic field in purple. And we also show in 4, 5, and 6, the exterior of Psyche beginning to freeze into solid metal, where the inside is still liquid. And it's that inside liquid metal that would be convecting and creating a magnetic field. In number 6, you see that one of the things we know from the meteorite record that happens when metal cores freeze is that sulfur that was dissolved into the liquid metal separates out into its own liquid. And so you got a yellow sulfur-rich liquid and then a red iron and nickel liquid. And that sulfur-rich liquid might very well erupt out onto the surface of Psyche. There's some chemical evidence that this might have happened to the parents of other iron meteorites that have fallen to Earth. And so we posit that that could have happened on Psyche. And then in 7, you'll see that there's some of that sulfur still on the surface. In 8, a mystery event has happened, presumably another impact, that's knocked Psyche over on its side, because that's the state Psyche is in right now. Its spin axis, instead of being perpendicular to the plane of its orbit, like our Earth's almost is, its spin axis is knocked over right into the plane of its orbit. So it's like a rotisserie chicken. This is important because we want to be able to take pictures of all the parts of Psyche when we get there, and we need sunlight to be hitting Psyche to take its picture. And so how it's spinning actually really matters. It comes into the mission planning process. So that's our cartoon. That's our cartoon of how Psyche was formed. And so I'm going to tell you a little bit about the process of being selected for flight. And I don't know if that happened in the previous lecture and the next ones, but it certainly has been dramatic and exciting, and I want to share some of it with you. This is the artwork for the cover of our Step 1 proposal. We were selected in the end as the 14th mission in the Discovery program, NASA's Discovery program. And in these big mission programs, Discovery and New Frontiers, it's a 2-step process. First, you write, in our case, about a 250-page proposal. It took about 40 people working for a couple of years to put together this plan. And this is the cover art. And now you know that we're trying to indicate this is the moment of one of those destructive collisions. And this is also art by Peter Rubin, the moment that maybe some of the core will be revealed. And then we were lucky enough to be what's called down selected. And there were 5 of us out of 28 proposals selected to go on to step 2. And in step 2, you have a year and you have to write an even more gigantic and more complete proposal. In our case, it was, I'm not quite sure, maybe 800 pages. And by the end of this year of step 2, we had 140 people working on the project. And there were other steps that in this step 2. One was the site visit, the famous site visit, when the professional NASA review board comes out to the location of our choice. And we chose Maxar, Maxar being our industry partner up in Palo Alto. They are building the chassis of the spacecraft. And we wanted NASA to know them because they had never been selected as a NASA partner for a deep space mission before. And oh, I see we need to mute. Oh, there we go. And so we spent a very, very intense, like life-changingly intense week preparing for the reviewers to come, with secret encoded emails with questions from the reviewers and practices and late nights and the whole bit. So this is the cover for our step 2, what's called the concept study report, the big long one, 800 pages. And you can see this is meant to be about 30 seconds later, where the impactor is screaming off to the bottom left and the rock is being stripped off this Psyche parent body, and you're beginning to see that red hot iron nickel core. So I hope that by now I've given quite a poetic and vivid image in your minds of how we might be seeing parts of the metal core of a tiny failed planet from the very beginning of our solar system when we go out in the asteroid belt. But here is about what we know of Psyche. We do not know what Psyche looks like. This is what Psyche looks like from a telescope from my backyard. My friends Patrick Young and Karen Meerman brought a telescope out and we saw it on one fortuitous night. But even from the Mount Wilson 60-inch, where we've also seen it, it's not much more than just a speck of light. We've been able to learn amazing things about this speck of light in the same way that we learn about other asteroids, by looking at faint interactions between that asteroid and other bodies so that we can begin to estimate its mass and therefore its density. And the density turns out to be a critical parameter. Psyche is perhaps the densest object outside of the really big heavy planets like Mercury. One of the reasons we think it's likely largely made of metal. We can also amazingly bounce radar off it from the big radar dishes like Arecibo in Puerto Rico. We can actually, this still blows my mind, we can send a radar pulse from Arecibo all the way out past Mars to Psyche, bounce the radar off of Psyche and have it come all the way back and receive the bounce. And by receiving the bounces of Psyche, of radar off of Psyche as Psyche rotates, and then by combining with that the changes in the visible light curve at the same time, clever people can make shape models of what Psyche's shape actually is. So here's one of our favorite shape models of Psyche. There are 3 or 4 out there that are all done by really competent teams of people. And we're looking at all of them as we plan our mission. They do not agree with each other. No, this is Vikenkoski et al. 2018. And it shows Psyche in different phases of its rotation. And then down at the bottom in the little dashed orange and yellow are areas on Psyche that they posit are maybe impact craters or places where mass has been lost. So they know the rotation pull and they know the approximate shape, each of the teams, and yet they don't quite agree. And so we're just making sure our mission works no matter what combination of these shapes it might be. But this is really what we know about Psyche. We know how light reflects off it and how radar reflects off it and how it interacts with other distant bodies. So we know something about its composition and its density, but we have never seen a metallic object. No human being ever has. And so this is one of the few kinds of bodies that has never been explored by people. And that's why it's so exciting. We do think it has to be largely made of metal, and it'll be the first time that humans have ever seen an object like that. So this is how big Psyche is compared to Arizona, where I now live, and LA down there, but LA to San Diego, it's a little bigger than that distance. And it's also just about the size of the state of Massachusetts. I've spent most of my adult life in Massachusetts, so I like to have Massachusetts in there. So although it's just the size of one of our smaller states, it's really one of the bigger asteroids out there. And it also makes up about 1% of the mass of the asteroid belt, even though there are almost 2 million known asteroids. Psyche's a big one and a heavy one. And that's about how big it is. And so let's say a little bit about how we might guess what it's made of. This is a schematic that I've drawn that goes over a little bit of the material I already have, but with a main point to make. So start on the left. There's just a lot of little bits, the riffraff of the protoplanetary disk, the big disk of gas and dust from which our sun and all of our planets formed. And so there are things in there called chondrites, which appear to be almost bubbles of lava from the early solar system, bubbles of melt, little pebbles of it. Calcium aluminum inclusions. They're called inclusions because we find them in meteorites, as we do all of these things. And calcium aluminum because they're very rich in those elements. And we think those are the very first solids to form out of the disk. They basically set the age of our solar system at 4.567 billion years ago, the very first solids, and dust and bits of gas. And these get crushed together in these turbulent disks into the planetesimals that we've already talked about. And the one on the left there, I guess you can see my cursor, I think. The one that's marked chondritic just means you can still see the chondrules in it. It hasn't melted. And then in the middle is one that has partially melted and partially differentiated. It's made of metal core. And then on the right, one that has fully differentiated. And that melting and differentiation is almost certainly because of the short-lived radioisotope aluminum-26. This is a radioisotope whose half-life is only about 700,000 years, so it is all long gone. It doesn't exist anymore. But it was common enough in the early solar system that it actually melted these planetesimals and allowed their cores to form. Everything I just said is learned from meteorites that fall to the Earth. And so on the right, you see this catastrophic impacts arrow. Some pieces of planetesimals, and maybe even a couple of whole planetesimals. It's possible that Ceres, the asteroid Ceres, is more or less an intact planetesimal. Vesta probably had a bunch of its exterior knocked off. Everything else in the asteroid belt is pieces of planetesimals. And the meteorites that fall to Earth almost all come from the asteroid belt in the current day. And so, it's just a few come from Mars, which is awesome, and a few come from the moon, which is amazing, and a few come from we don't know where, but almost all the rest of them come from the asteroid belt. And so all these things fall to Earth, and it's this library of material from the asteroid belt. So we start using that to try to guess what Psyche might be made of. So here are meteorites from differentiated parent bodies. So I've got my little differentiated planetesimal in the upper right to remind you. On the left is the Alvord iron meteorite, and that's really completely accepted, I think, by everyone to be part of the metal core of a planetesimal that differentiated. And the beautiful, beautiful cross-hatching is actually intergrown crystals of iron nickel metal that happen as that core cools over a very, very long period of time. This is a pattern of minerals that never ever forms on Earth. There is no big body of material that forms and cools under the same conditions as a planetesimal core does. And so that is just from space. And that pattern is named after the early scientist who first described it. It's called the Widmanstätten pattern. And you can even buy jewelry made out of common iron meteorites that has that pattern in it. We think that could be part of what Psyche is made of. And then on the right is part of that rocky fraction of a differentiated body, in this case, Vesta. This is a meteorite that we know from its spectra, from the way light reflects off it, that it came from Vesta. Here is a more obscure meteorite. This is a meteorite called a palisite. It was named after an early geologist named Simon Pallas, who found one of the first palisites fallen, I believe, in Russia. And it is a mixture of the gray iron nickel metal, and then the little yellow and black pieces are silicate minerals, pyroxene. And it's thought to be the core mantle boundary, the boundary right between that metal core and the rocky exterior of a planetesimal. Meteorites like this one actually match the density and the reflected spectra of Psyche. So it's possible that Psyche is made out of material like this. And then finally, it's remotely possible. Oh no, I have two more to do, not quite finally, penultimately. It's possible that Psyche never melted, that it's unmelted primitive material, highly reduced, so almost no iron oxide, almost all of the iron in metal phase. And one of the meteorites that it doesn't match Psyche as well, but it's still kind of a possibility, is the enstatite chondrites. The reason that is exciting is because the enstatite chondrites, again, if you are not a meteoriticist, it's quite off-putting, the names of these meteorites. And I joke that it's just jargon to keep people out of the field. It just means that it's an unmelted material that contains the mineral enstatite. And so this comes from an unmelted primitive body. And these meteorites are thought to be the material from which the Earth was formed. There are a lot of arguments around the isotopes of the elements matching those of the Earth. It's possible that Psyche is the parent body of some of the material that actually formed our Earth. But an even more exciting possibility for any of you who are budding meteoriticists, there's a group of meteorites called the CB chondrites. And chondrite again means that those chondrules, those bubbles of now minerals originally melt, never were remelted and differentiated. They are just the primary material from the early solar system. These are very strange chondrites because they're extremely high in metal. You can see all the shiny silver metal here. And no one really understands how they're formed. There are a whole bunch of different ideas, none of which are really definitive and none of which can quite be proven. And there aren't very many CB chondrites, so they're not well understood. No one knows where they came from, and they're rare. But these are the materials that most closely fit Psyche, both in reflected spectra and density. So it is possible that Psyche is made of CB chondrites, which I'm hoping is a little bit exciting to you if you've never heard of them before. And if you have heard of them before, then it's actually pretty interesting. So CB chondrites, that's a bizarre thing that could be Psyche. So what I've just told you over quite a few minutes is that we do not know what Psyche is. So let me talk for a moment about the mission process. Back in 2011, I had the first discussion about what ended up being the Psyche mission. I and my colleagues Ben Weiss and Maria Zuber had published a paper about how planetesimals form and how cores form in them. And it was a controversial paper, which made it really fun. And I got an email from some scientists at Jet Propulsion Laboratory saying, we would like to propose a mission to test your hypothesis. So then over the next 2 years, I spent a lot of that working with a team of people that we built very slowly, selecting where we would go to test the hypothesis. We settled on Psyche, convincing Jet Propulsion Laboratory to be our NASA mission manager, because it takes a big set of resources from them and a dedication to go through the proposal process. So they only want to propose missions they think are fairly strong. And then so AO here stands for Announcement of Opportunity. So that's when NASA sends out a giant call saying, we are going to accept proposals to the Discovery program, and this is all the things you need to do to propose. But you can see there are only a few months between the release of the AO and the step 1 proposal being submitted. That is not enough time to write a mission proposal. So we had to basically have written our proposal, selected our partners, built our mission team in early 2014 to be ready to propose in 2015. And I will say, just in case this is, I don't know, in any way consoling or connecting for any of you in this difficult year, in the middle of 2014, I was diagnosed with ovarian cancer. And so I was going through chemotherapy and starting a brand new job at Arizona State University as the director of a great big school and writing this proposal. And I will say that the thrill of writing the proposal and the hope that it brought with me was an incredible motivator. So I'm very lucky I got through both of those things. Amazing. So at the end of 2015, we were told we were moving to step 2, and then we did that step 2, the concept study report, the big long one. We did the site visit, And then in early 2017, I got a call from the NASA associate administrator saying we were selected for flight. And you could have knocked us over with a pin. We were not going to be selected. We were the underdog for every reason. And so we were really quite shocked. And now we're in that amazing NASA process, phase B, phase C, phase D, phase E, and then finally getting to Psyche. So PDR is a big review, CDR is a big review. We did the first ever virtual CDR, critical design review, back in May, the first virtual one NASA had ever done. And now we're there, really about to go into phase D. We are building flight hardware every day. Our schedule is 21 months to launch, and we are very tight. So far, we're still okay. COVID has not killed us. We came in strong, we're doing great, and we're intending to launch in August of 2022, and then doing a Mars flyby cruise for about 3 years, arrive at Psyche in early 2026. There are 5 science objectives for this mission. The first one is the one you might be able to predict yourself by now, determine whether Psyche is a core or if it's primitive unmelted material. And we do not know the answer to that. We're going to use all of our instruments, the magnetometers, imagers, the gamma ray and neutron spectrometer, which gives us the composition of Psyche, and also gravity experiment. Objective B is to look at the relative ages of surface regions, and we'll do that by counting craters. The ones that are more cratered are older. Again, this is just an artist's impression. We have no idea if Psyche is going to look like this. And let me just state again really clearly, probably everything I tell you that we think we know about Psyche right now will prove to be wrong, because space always surprises us. And our curious imaginations, as broad thinking as we can try to be, we never think of all the things we're going to see. And so probably when we get there, it's going to be something completely different than what I'm describing. I'm skipping objective C and D because they're really specific geochemical ones about oxidation state and light elements. And then objective E is a really fun one. Just characterize Psyche's morphology. What is the shape of it? These are pictures of Ceres on the right and Vesta below, are their models, their topographic models. What do impact craters look like in these rocky and icy bodies? How big a mountain can be supported? Do faults exist? All these kinds of questions we'll be asking about Psyche, about brand new material. This is a high-speed impact to make a crater into a piece of iron meteorite done by Simone Marchi with the Ames vertical gun. And that's my thumb for scale. And what I want you to notice about this impact crater is it does not look like impact craters in rock or in ice. It has overhanging flaps of frozen metal. It has concentric cracks in the crater and radial cracks outside the crater. So we expect to see something quite unusual when we get there. This is our picture of the actual plans for the spacecraft. So the mission's led by me at Arizona State University. Our mission manager partner is Jet Propulsion Laboratory. Our industry partner is Maxar. They are building the chassis, and we've gotten really far with it. We've got space hardware, it's so amazing. And the solar electric propulsion system. And then we have many, many other partners, including Johns Hopkins Applied Physics Lab building the gamma ray and neutron spectrometer, Malin Space Science Systems and Arizona State University for the cameras, the imagers, and Danish Technical University is building our magnetometers. So this is what the chassis looks like with a person for scale. It's actually huge. It's a couple meters, several meters on a side. If you look on the left and you see this superstructure, these booms out the top, up at the very top is the gamma ray spectrometer. Now, one thing you'll notice that's different between Psyche and the other missions is that we do not name or give acronyms to our instruments. We just really wanted to call them what they were so that no one would be confused and everyone would understand exactly what we're talking about. So our gamma ray spectrometer and our neutron spectrometers are called those things. They don't have another name. Those instruments measure the atomic composition of the surface of the body by measuring the gamma rays that are emitted after nuclear reactions with galactic rays. It's the most amazing process ever that we can use these intergalactic rays that come through and hit the surfaces of airless bodies and cause the atoms in them to give off gamma rays that we can then sense and know what kind of atom it was. There's a high X-band high gain antenna. The deep space optical comm on the left DSOC, is a tech demo. It has nothing to do with our science. We will not be running it while we're at Psyche, but while we're near Mars, we will practice receiving laser communications and sending back laser communications from the Psyche spacecraft instead of using radio. We get a lot more bandwidth. People joke it's Netflix for Mars. So this is a tech demo we're running. On the right, you can see the magnetometers up on a boom and the cameras looking out the back. And the bottom, you see the SPT ion thruster. So this is a solar electric spacecraft that is propelled by ionizing the noble gas xenon and sending individual xenon atoms out these thrusters through a little potential field. And the little bit of impulse that the loss of every xenon atom gives is what drives the spacecraft forward. It's incredibly efficient. We're going to fly 960 kilograms of xenon. And when we unfold our solar panels, there we are, the size of a singles tennis court, almost 25 meters long. It's going to be amazing. We are launching sometime in August of 2022 on a SpaceX Falcon Heavy. And SpaceX does intend to land the boosters. And so to say that I'm looking forward to this day, getting there is hard. I mean, if we have another giant COVID crisis or more brush fires by JPL, it's possible that we won't make our schedule, and that would be catastrophic. We are doing everything in our power to make our schedule. We're still good to do it. We're planning on being on that Falcon Heavy in August of 2022. Then we will, if you look at launch in the mid-right on the screen, we will launch off the Earth. We'll start practicing with deep space optical comm almost right away, and thrusting where there's gray over the trajectory. We'll do a Mars flyby in 2023, and then we will zoom out to Psyche, arrive in Psyche at the top of the picture in January of 2026 and start orbiting. We will orbit for 21 months. We will orbit through different surface lighting conditions, and even through conjunction with the sun where we can't see Psyche from where we are. I thought I had one more. I will just wait for a moment. We're going to step through 4 orbits, A, B, C, D, getting closer and closer to the surface as we learn more and more about the shape and gravity of Psyche and getting better and better data. So the last thing I want to mention is we have significant student collaborations. NASA challenged us to do more and better on the student collaboration side than had been done. I'm very proud of what we've done. Whether there's time across the bottom of the chart, starting with our selection in January 2017, right up to the May of 2021. So we're looking through the whole school year ahead of us. And the vertical axis is number of students. And every single horizontal red line is 1 student. You can see we have some students who've been with us almost from the beginning. And then we have a lot of students that just come and join us for the school year. It's actually higher than this. We have about 850 students who participated in Psyche mission projects already. We have 4 different main programs. We have a big capstone program with interdisciplinary teams, so students learn how to work with project managers and graphic designers and marketers. And we have an art program I'll tell you about in a minute. We have free online courses that you can find through our psyche.asu.edu website, free to everyone in the world forever. One about the process and timeline of a NASA mission, and the next one about how to create inclusive teams. The third one will be out sometime this year. It's about the small bodies of the solar system. And then finally, we have some K through 12 docents who do a lot of work when people are in school. One story about artwork as my very last thing. We have 16 students that compete and are selected each year, a new cohort of Psyche Inspired artists. These are any undergraduate at a 2 or 4 year institution in the United States. They do not have to be American citizens, but they have to be at an American school to apply and be selected. And they create 4 original pieces of art inspired by Psyche and exploration in the future of humans. And we create books and exhibits and websites. And this particular person was a ceramicist. And this platter is quite large, maybe 2 feet across. And he wanted to make a glaze that in his mind was like the surface of a metal body. And so he combined iron filings and a material called thermite, which if you know what that is an extreme heat producer, almost explosive. And he put it in the kiln. I did not know about this till later. Kiln did not blow up. The thermocouple was triggered, it turned off, but the glaze completely worked and it bubbled up and made this amazing, amazing glaze on this platter. And so that is my short story about Psyche, the journey to a metal, we think, metal world. We're on Twitter at NASA's, oh no, sorry, that's not our Twitter handle anymore. I didn't fix this. On Twitter, we're Mission to Psyche, and I'm still LT Elkins on Twitter, and that's our website at ASU. And here's another of Peter Rubin's amazing images for what Psyche might look like. So let me stop sharing, and then I would be so happy to answer any questions that you have. Let me see if I can get back to stop share. There we go.
Great. Well, thank you, Lindy. Thanks so much. We have a few questions that have come in already. One is, are there any plans to research asteroid Moa?
Oh, Oumuamua.
Yes, there you go.
Yeah, all right, so for those of you who do not know about this coolest thing ever, so after 50,000 years of humanity or whatever, however you want to count it, suddenly in the last couple of years, we've noticed that objects have been flying through our solar system that do not belong to our solar system. They're not gravitationally bound to our sun. And when you trace their trajectory, you go way off into space, someplace else. And so 2 of these have been seen so far, flying suddenly through our solar system, like these weird guests. The first one was named Oumuamua, and we just have like really vague little pictures of it. We weren't quite ready. And oh my gosh, would we love to study Oumuamua, but it is long gone and there's no way for us to study it. And isn't that sad? So now we just have to be way more ready for the next one.
Here we go. What are other Earth-based observations are planned for Psyche before arrival?
Oh yeah, people keep looking at Psyche. In fact, I was part of a team that looked at it with the Hubble Space Telescope to look at its light curves and see if we could tell anything about what it was made of. More radar observations, observations of its thermal inertia, how quickly it heats up and how fast it cools down. That would be pretty diagnostic of metal. And there have been a couple of measurements done that way, and they completely disagree with each other, and their error bounds do not overlap. And so we have no idea what the thermal inertia is. And so I don't know of all the different things that people are planning, but those are some of the things I know are coming up. And it's one of the exciting things about being selected for a flight project is that suddenly there's so much more motivation for the scientific world to study this object, because everyone can make predictions about what it is, and then they'll find out instead of never knowing. And so it's a really, really great situation for new science.
Great. What platform is hosting the ASU courses you mentioned?
It's hosted through continuing education at ASU. And if you go to psyche.asu.edu, you'll find the link to the courses there.
Great. If we don't have an idea about Psyche's shape and gravity, how is the trajectory designed for the spacecraft being done?
That's a great question. I know. How do you make the plan? So there are, we published a paper earlier this year in the Journal of Geophysical Research, putting together all the data that had been published about Psyche so far. And there have been, I haven't counted, 10, 15, 20 density calculations of Psyche. And now there are, I think, 4 really good shape models from very, very good meticulous teams. And if you take any given shape for Psyche and you imagine that you take that volume and make it into a perfect sphere, the radii of those spheres agree within a few kilometers of each other. So we have some kind of idea of its size. I would say there's between a 10 and a 30% error on its density measurement right now. So we have some ideas. And we definitely know how to get there, because we know what the Psyche asteroid's orbit is. That we got. The hard thing is, once we get there, how do we get stable orbits? NASA requires that any orbit that we put our spacecraft into has to be stable for, I forget, 20 days. Someone online probably remembers the exact number. So it has to be that if we put it in an orbit and then the spacecraft goes into safe mode because of some software error or like make up a thing, that spacecraft's got to orbit safely by itself for a while. We just can't put it in a situation where the minute we lose touch, it'll crash. And so calculating those stable orbits requires that we know to a very high fidelity the shape and gravity field around Psyche. And so that's part of the reason why we're stepping down from a high orbit to a close orbit. And these are operations that were learned and practiced with the Dawn mission at Vesta. And so we are taking a lot of lessons learned from them, and we won't step down into a lower orbit until we know the gravity field incredibly well. And so our reviewers asked us a similar question to what you asked us, which is, how bizarrely shaped or how weird could the gravity field of Psyche be? What's the extreme case, and can you still prove to us that you could find a lowest orbit that will work? We need an orbit of a certain height to get the measurements we need. So we ran 5,000 Monte Carlo simulations of different shapes and gravity fields of Psyche to show that we could always find an orbit that worked.
Excellent math. Crazy, huh?
Love it.
How old is Psyche? Is there any regolith on its surface?
Oh, what a great question. No one knows. No one knows if there's regolith on Psyche. I have a graduate student named John Christoph, a young man who came to work with me on Psyche mission. And this is what he's trying to discover. Does metal make a regolith? And so if you imagine, you look at the moon, or you look at Bennu, exciting Bennu that we're about to go visit, or any of these rocky bodies, and they're covered with dust, pebbles, cobbles, little tiny bits of rock. Those are caused partly by the gardening effect of lots of little meteorite strikes, breaking it up, and also by the solar wind. So the solar wind actually breaks silicate rocks into little grains. So the question John's asking is, what do these things do to metal? It looks like solar wind does not break metal into grains. Solar wind almost makes metal stronger. It does not break it into grains. Meteorite impacts can splash or break off little tiny pieces of metal. So there could be a metal regolith, a metal soil. By the way, I've always been very meticulous about using regolith for planets that have no organic matter, and soil for the same material that's mixed with organic matter. But the International Soil Association, or whatever its proper name is, decided a few years ago it was fine to call regolith soil. So we can actually call it soil on the moon, which sounds so wrong to me. So we don't know if Psyche has one or not. It could be partly a rocky regolith like on the moon. It could be little bits of broken metal. A very, very cool possibility is something that Jay Balash, who we very sadly lost this year, a fantastic geophysicist, planetary scientist, he pointed out to us that at very cold temperatures, metal breaks like glass. And so the side of Psyche, the pole of Psyche that's facing away from the sun during part of its orbit, would get very, very cold. And it's possible that impact craters on that side would just cause it to shatter like glass.
Interesting. Now that will be one crazy thing to get images of once we get there.
I know. I know.
Why are they so amorphous? The planets and satellites are more spheric.
Oh yeah. Why are they those funny shapes? Well, what are the reasons that something becomes a sphere? The main reason is through its own self-gravity. If it has enough self-gravity that it pulls hard enough on all of its material, the material settles into the lowest energy state where it's all as close to the center as possible, and that's a sphere. But in order for the material to do that, it has to be able to flow. So you need two things. You need enough gravity and material that can flow. And so you either need a solid planet that's very large, and at the high pressures of its interior, the material even flows in the solid state, which is what happens inside of the Earth. Or you need a tiny body that's been molten, and then as a liquid, it can flow into a sphere. And so most asteroids actually, they may or may not have been spherical to begin with when they were planetesimals. Depends on if they melted or not. But now they're all funny shapes because they were broken after they solidified, and they don't have enough gravity to pull themselves into a spherical shape because they're too small.
Great. And someone would like to know, how does a college student get selected to support Psyche?
Oh yeah. So first of all, let me just say, it is my mission to get as many people involved as possible, whether as like friends of the mission who are just watching what's going on and following us on social media and interacting, or people who are really involved. There is, however, a limit to my powers, because our job right now is to use every penny to build the spacecraft and get it launched. That being said, the 4 student projects that we have running, you are so welcome to apply to. And so you can apply to be part of the art program, Psyche Inspired. You can take the online courses. The third good opportunity for someone who doesn't happen to live in Phoenix, which is just where our K-12 docents program is, only just in Phoenix. It's just a few students. But the third one is these capstone programs. So this is for project-based learning that happens in many, many universities. And we give you real problems from our mission, things that we actually need to have solved. And if you want your university to participate in the Psyche program, talk to the people who teach the capstones and invite them to be in touch with us. We have more than 50 capstone teams at over 20 universities right now. And as you see, hundreds of students involved. So that's a good way to do it. There will be more ways going forward. We have a really cool plan we're trying to put in place to show amateur people how to build a receiver so that they can receive the laser transmissions from the deep space optical comm on the Psyche mission. That would be a great thing to do. And then we'll have competitions as we get closer for what Psyche is going to look like. And we're going to invite people to submit in any format that they want their idea of what Psyche might look like. And then we'll have judging panels and all kinds of prizes and things. And then finally, I'll just mention that space exploration is for all of humankind. We do it to inspire everybody to be bolder in our own lives here at Earth, here on Earth. And NASA's very correct policy is that all of our data becomes public. Usually that takes a few months. Usually the mission is allowed to interpret the data and publish and then release. But we've decided, Jim Bell, who was the deputy principal investigator of the mission and the lead of the imager, the cameras, he and I have decided that we're going to release all of the images that we get right when we get them. And so the very first pictures we get of Psyche, we're going to have them on the internet within 30 minutes. And so everyone in the world, you included, will be able to look at it and wonder at the same time as we do, what is that?
Very cool. Very good. That's awesome. And all your stuff you got going on for ways for people to get involved are fantastic. I dare say out of this world. Yeah, that was horrible. Are there any known moons of Psyche or other hazards to navigation?
Yeah, no, we've not we, I shouldn't say we, because in this case I wasn't involved in any way. Other astronomers have done very, very careful observation campaigns of Psyche and have limited the possibility of moons down to very tiny things. And we will also be scanning. As far as we know, there are no hazards to navigation.
Phew, that's good.
Yeah.
Any long-term plan to consider harvesting of asteroids for metals or water?
Yeah, many people are planning these, and I personally think it's a great idea. There is only one Earth, and Earth, as we all know, is under great stress, and it's becoming less and less habitable for humans. And I'm here to tell you that it does not matter how much damage we do to the Earth, it will always be the most habitable planet we can reach. No matter what we do to Mars, it's never going to be better than the Earth. And so we have to take care of the Earth, and using meteorite or asteroid resources is very smart. It won't be Psyche though. Psyche is too far away. It's really not practical to bring stuff back from Psyche and use it economically on the Earth, but there are near-Earth asteroids that can be used that way. And I will say that there's a persistent story out there about how valuable Psyche is and how NASA and Elon Musk are rushing out there to grab it all for themselves, which is so ridiculous. Our mission is purely about science. We're not even touching the surface. We're absolutely not able to return anything from that distance at this price point. It's pure science. But we hope to learn more about what the materials are, and then we can eventually take advantage of closer asteroids.
Well, how will Psyche end? Is it going to impact the asteroid? And if so, will you have a high-rise flyby before doing so?
Yeah, that's our, at the moment, that's our end of mission plan, is just to get as close as we can to orbit down and down and down and down and eventually to hit the surface. And we're not allowed to use the word land because that has a lot of a lot of implications, like you continue to transmit information to Earth afterwards. But we will go down as slowly and gently as we can to get us data as far down as we can. We don't have any plans right now to leave Psyche and try to look at another object. There is not another object nearby for which that makes sense. And so, but things can change between now and then. It's many years in the future.
And if not Psyche, what other objects in the asteroid belt should we study in the future, and why?
You know, the asteroid belt is filled with things that we don't know about yet. And so Psyche is one of the outstandingly weird things that'll tell us not just about, we think, early planet formation, but also the Earth's core, which we are never going to reach no matter what Jules Verne says. It is not reachable. And so this is the only way we'd ever see metal. There are other bodies in the asteroid belt that are mysterious and fascinating. And I should think that one of the next big sets of targets will be additional comets. The whole story of how volatiles are moved around in the solar system. We've learned a lot about the rocky ones, but not as much about comets. Although I have to say the next thing has got to be the atmosphere of Venus.
Oh, yes. Venus would be awesome.
Yeah.
Is Psyche the only asteroid observed as primarily metal?
We think that there are 9 asteroids that are primary metal that we know of, but there's the next biggest one is a fantastic asteroid called Cleopatra that is it's about 50 kilometers long, so it's about 1/4 as wide as Psyche, but it's shaped like a dog bone. It's very, very thin. It's like something that spewed off when it was in the molten phase. And that's the next biggest one, and the other ones are really tiny. So Psyche is the only large, relatively round metallic object that we know of in our solar system.
Wow.
And we'll get there and watch it not be metal. Watch it be something totally bizarre.
No, it has to be metal because you've built this up and about how weird this is going to be. So it has to be.
It's either going to be metal or it's going to be something so weird. Yeah. It's not the Death Star. I've been told very clearly that the Death Star plans have a different radius than Psyche.
Oh, very well. That makes me feel better.
Yeah.
From the in situ observation data, how will you know when and how the asteroid Psyche was magnetized?
Right. So we've got these 2 beautiful magnetometers being built by Danish Technical University, and they're hanging out on a boom on the top of Psyche, one halfway up the boom and one further. So that's called a gradiometer configuration. It allows us to subtract out the magnetic field of the spacecraft. And so we'll be measuring magnetic field every minute, all the time. And what we hope is that we'll be able to measure a field of magnetization around Psyche, and that we'll get a really lovely complex map of it and details as we get closer and closer. So if Psyche froze from the outside in, if it was a core and it froze from the outside in and it created a magnetic dynamo, then the outer about 20 kilometers should have been magnetized permanently. And so we hope to see regions that are magnetized at strengths that match the models for that dynamo. It is also possible that if Psyche was molten and crystallizing in that way, it could have obtained some magnetization from the disk, from the dusty disk, but that would be a different strength of magnetic field. So at the moment, our thought is that if we measure a strong magnetic field, it's proof that Psyche was a core. And if we measure no magnetic field, it proves nothing. So that's where we are with magnetic field.
We have a couple more questions in about 5 minutes, so I think we should probably be able to get through these. Have you observed a tail with Psyche? And if you haven't, but if you would expect one, what could you observe that would be unique?
No, that's interesting. No, there's no tail on Psyche, and no one's even been able to see any dust around it. Normally for a tail, you'd want something that was coming in closer to the sun and it was shedding volatiles. And none of the observations of Psyche show a significant signature that it would have any volatiles on its surface. There's one spectral observation that says that something on the surface might contain oxygen and hydrogen bound together. That could mean, if it's a correct measurement, the most likely explanation is that an asteroid bearing minerals that contain water in their silicate structure crashed onto the surface of Psyche and left it there like detritus. But we don't have any indication that the body of Psyche has anything that it could shed as a tail.
And okay, so a regolith question again. If Psyche turns out to be metallic, can you speculate on the possible physical properties of a metallic regolith?
I know, isn't that great? We've been trying to speculate, and there's so little to speculate upon or with. One interesting thing is for the rock part of Psyche, we could expect it to be similar to other rocky asteroids. So that part is not too bizarre. But if there really are metal parts, and if the only way you make a metallic regolith is from little shards that are broken off during impacts. So on the Earth, when there's a big impact, rubble, like pieces of rock, are thrown off in the solid state, but also liquid is created, a melt pool from the energy of the impact if it's big enough, and little bits of melt are flung off. Those are called tektites. And so they're frozen drops of magma. They freeze while they fly. They're really interesting if you haven't run into them. And so would we see these things made of metal? Yes, we would, from the range of sizes of impacts. And so we have some idea of what the little brittle unmelted pieces might look like, because they fly all over the chamber when people do experiments at the Ames vertical gun, like Simone Marchi did. So we collected as many of those little metal shards as we could, and John Christoph is analyzing them. And one of the things you can do is look at their size and shape, and then estimate how they would pack together, and could they actually form steeper hill slopes or other kinds of shapes of regolith. And so that's a really interesting thing to think about, how much they would interlock, and they would interlock much more than would silicate mineral grains.
Fascinating. My first thought was like aluminum or iron filings.
Yeah. Yeah, right. Are they going to be needle sharp? What's it going to be like? It won't be good.
Okay. Oh, here we go. Can any country or institution claim any rights over asteroids?
Oh, that's a very hotly contested thing. The country of Luxembourg is setting up to be kind of the arbiter of that. At the moment, there are some areas of agreement around the world about these things, but it's not universal. And frankly, if I could just get on a sort of utopian soapbox for a moment, this would be a great moment for humanity to get this right, because we can be our better selves in space, and we can explore in a way that is ethical and inclusive. So let's all push our legislators when these things come up.
Okay, very good. All right, well, that brings us to that's an hour. So we're going to go ahead and stop for the evening. So thank you very much, Lindy, for your time this evening and talking to us about Psyche. And thank you all for your questions. Good questions, good discussion that we've had here the past half hour or so. I invite you to, or just reminds folks, this was recorded. And we will post that recording to the LPI YouTube channel once it's ready, probably within another week or two. It should be good to go. Our next presentation will be November 12th, that Thursday evening, with Dr. Jennifer Heldman from NASA Ames. She's going to talk about the Viper mission to the moon. It's a robotic prospecting rover that's going to go up in the next few years. So that should be another good, interesting talk as well. So thank you all again very much for joining us. Lindy, any last minute thing you want to you want to share?
Thanks, I did. I just wanted to thank you for inviting me and everyone for coming tonight and asking such great questions and saying such nice things in the chat. And I wanted to just give a shout out to my friend Alan Treeman I see there. And I'm sure I have other friends in the list who I just don't happen to see their name right now, but I saw Alan and his greeting. So thanks for all your kind words and your questions. I just enjoyed this a lot.
Great. Well, thank you all so much, and everyone have a good night.